Alright, welcome back. Today we have text problem 43-10, a suggested problem for lesson 3. So let's get into it. First thing I need you to do is get a scratch piece of paper or a blank printout of the problem to follow along. I'm going to go ahead and get the physics problem solving format set up. I want you all to pause the video and do the same, and I'll see you in a few minutes. Alright, welcome back. So as we look at our physics problem solving format as we have it set up right now, from the read step I saw that we have energy released in this nuclear reaction and it is a fission reaction. So that should point me back to our Q value as you learned from your reading. Now the draw step, unnecessary, but you can see that as the neutron comes in, it's absorbed by the nucleus, it becomes unstable, and just like we saw in class with the flipping of nickels, it is a completely random event, but in this case the fission reaction has occurred. Two daughter particles have split off, as well as two additional neutrons. Our given information is seen above with the atomic masses and particle masses. We don't have to make any assumptions. Our task is to calculate the Q value, or the energy released, in the nuclear reaction. So as we look at our physics step, we're looking at the equations we're going to need to solve or achieve our task. So because we're looking at energy released in a nuclear reaction, we're going to use our Q value equation. So the energy released in a nuclear reaction is equal to the negative change in mass energy times the speed of light squared. So if this is what you have set up and what you work towards, great job. If you missed a couple steps, then keep practicing at it and you'll be pros in no time. Now as we get into our solve step, you now have seen this delta symbol twice now. Once with this equation and once with the change in binding energy. Whenever you see that delta symbol that's in front right here, that's going to represent the change in something. Now, the way we represent it in this class, it's going to be our final value minus our initial value. So as we're looking at the change in mass energy, or specifically delta M is just the change in mass, we have our final mass minus our initial mass. Now our final mass in this situation are the products in our nuclear reaction, and our initial mass are the reactants in our nuclear reaction. So in this case, M sub F, or our final mass, is going to be the sum of all of our mass energies on the right hand side of the reaction. And our initial mass is going to be the sum of the mass energies on the left-hand side of the nuclear reaction. So now that we understand what our symbols mean, we can go forward and actually start putting our information into our equation. So I want you all to pause the video. I want you to work ahead, and at this stage you don't have to put in numbers. Just put in the symbols that represent the masses. And once you've checked your work, then we'll go to the next step of actually putting in our given information. So pause the video and I'll see you in a few minutes. Alright, here is our algebraic solution. We have our final masses added up from the right hand side of the nuclear reaction minus the initial masses from the left hand side of the nuclear reaction. And then we have our shared constant, c squared. And now from this point we can actually put in the masses for our individual atomic masses or particle masses. Now you could do one more step of simplification. Notice that we have two masses of the neutron, and here we have just one. You could simplify, reduce this down to the mass of one neutron, and take this out of the equation, but how it is set, it tells a story that you have your final minus initial, which gives you the total energy released in our nuclear reaction. So go ahead and put in your given values, and you can check back and see what your answer is here very shortly. All right, I will see you in a minute. All right, so I broke this up into two steps. First, I added up all of the masses involved in our nuclear reaction, and then I multiplied that times our constant for speed of light squared, and then I got to our answer. The reason I put it into two steps is I wanted to show the fact that the sum of our masses involved in this nuclear reaction are actually negative. That means our final mass, the sum of our final masses, is less than the sum of our initial masses. So that's telling you you start with 5 marbles in your hand, the nuclear reaction takes place, and there's only four marbles left. So the question is, what happened to that 5th marble? Well, in this case, instead of marbles, we're talking about mass. It's turned into energy, and generally in the form of heat, or it's in the form of kinetic energy. And I know we haven't talked about kinetic energy yet, but this neutron coming in is absorbed by the nucleus. It decays or fissions into 2 daughter particles, as well as 2 neutrons going off that can create a chain reaction. But the speed of these neutrons is not the same as this initial neutron. So the change in mass energy has turned into pure energy in the form of either kinetic, or it's turned into photons and thermal energy. So there's lots of forms of energy, but that's what's taking place. So we can isolate that by saying our final minus initial we expect to be negative. If we multiply times a negative sign on the outside, it tells us how much energy is released in the reaction. And so that's why we have this negative sign out in front of the right-hand side of our equation, and that's why we end up with a positive value when we look at the energy released in the reaction. So if you compare this energy released in a fission reaction to text problem 37-44, where we have much smaller nuclei, we can see that we're looking at just tens of mega electron volts, whereas here we have 180 mega electron volts. A stark difference between those reactions, and why we choose to use things like uranium-235 to power our nuclear reactors and not something much smaller. But we'll have plenty of time for that in class. I will see you next time, and happy physics!